Grzegorz, me, and thank you for invitation. I would like to give you some presentation about my last research concerning the energy harvesting. Today I'd like to tell something about two different approach of energy harvesting in the magnetostrictive material and the composite material with MFC piezo elements. So the first is the first presentation concerning the energy harvesting of the magnetostrictive beam modern base of Galfenol alloy. And the outlet is introduction. I will tell something about the modeling, mathematical modeling, and the numerical solving this model, the analysis of the results, and we have done several measurements in labs to confirm our mathematical model, and finally the conclusions. Okay, so generally the magnetostriction can be described most generally as the formation of the body in response to a change in its magnetization. This phenomenon is reversible and can be used to generate flux change in the alloy. So, and here I'd like to show you the our mathematical model, which is visible on the figure A. And the system consists of the intercoherent substructural beams. This is aluminum and magnetostrictive layers with the neutral stress axis, which is given here in figure B, shifted away from the axis of the symmetry of the magnetostrictive beam, which is shown here. The coil that generates the electromotive force is mounted on the beam close to the supporter. The advantage of the magnetostrictive materials comes from their magnetization, a property which occurs and changes under mechanical stresses acting on the material with reversible properties. In the analyzed model here, there is a reported sensitivity of the system to the initial conditions, and it was compared for the first three resonance zones of this vibration beam, leading to the determination of two types of solutions with different levels of power output. And at the beginning, I'd like to introduce something mathematical approach. So introducing the magnetization to the element of the magnetostrictive material by the magnetic flux density, which is shown by dB, one can get the magnetic work shown by equation 1, where H means the magnetic field, and simultaneously affecting the mechanical strain to the magnetostrictive part of the beam. The mechanical work is delivered to the magnetostrictive element. It is written by W2. And taking into account the reversible system, the internal energy charge is equals both of them, and the general dependencies concern the magnetic and mechanical behavior of the magnetostriction. By, of course, we have to here neglect the thermal effects are described by the constitutive equation, which is shown by equation 4, and more detailed in the equation 5. Okay, this is a well-known formula, so maybe I missed this explanation. And if the relationship between this term, if in the constitutive equation are linear, because this constitutive equation has to be linearized, then the internal energy in the magnetostrictive material of cross section on the length Tx is equals as shown by equation 6. Of course, substituting the constitutive equation to this form of the internal energy, one can get the pure energy of the which is generated in the magnetostrictive material. And the first term is called the pure elastic internal energy. The last one, the third one, calls the pure magnetic internal energy, and this in the middle is called the mutual magnetoelastic energy. That is shown here. There's three parts of this energy in the magnetostrictive material. Okay, so using the derivative of the strain energy U of this U with respect to the electrical current I, the coil. In the coil, of course, one can get the magnetic flux, which is shown by equation A, and that first term describes the magnetic flow generated by the stress on the which react on the beam. It comes from the bending, of course, moments while the system is vibrating. And the second term represents the charging process while applied current I flows. It also includes the equivalent inductance associated with the pickup coil around the magnetostrictive material. Okay, so in case the system is vibrating and the applied current equals 0, then generated magnetic flow phi m is equal as from the equation 8. This is called here, and taking into account the generated magnetic flow is proportional to the current flow with respect to the inductance L, as form is here shown. Finally, the generated current by the pickup coil during system vibrates is equal as given here. So finally, connecting these three equations, we can get the formula for the voltage while we introduce both these equations to this magnetic flow and make the derivation over time. According to the Faraday's law, we can get the formula for the voltage, which is generated on the magnetostrictive material, of course, on the coil. And in this equation, one can get the mechanical stress, and there's the bending moment, which is which is correlated to the Young modulus and inertia moment of the cross beam of the magnetostrictive material. And here is shown the deformation of the magnetostrictive beam under the bending moment is acting. One can get some stresses from the neutral axis, which change due to if the radius is increasing. So finally, introducing all the previous equation, one can find the equation of the voltage, which is given by equation 14. And there is integral where is included the function of the shape function of the beam while the system is vibrating. So this function it depends of the distance and the time. So finally, we can introduce the two functions, which the first is connected with the displays of the points of the beam, at the second only on the time. And now, of course, the first part of this formula for let's say assumed point P for the position of this point. This first function is describing what kind of mode is during the vibration, if the system vibrates with the first mode, second, and the third. So we use the general solution for the analyzed shape mode by equation 17. And there are some lambda function which is calculated from the transcendental equation. It was found numerically, and for this three modes we calculate these values, and we have the formulas to the equation of voltage for this three kind of behave of the beam. And finally, we use the Lagrange approach to derive the differential equation of motion, and there is shown here. The first equation considers the mechanical differential equation of the beam motion. The second is electrical equation, and both of them are connected by parameter g, which is called equivalent gyrator, which converting mechanical relative velocity of the point of the beam into the voltage V. So we can see G in the second equation, and the first here, which is multiplied by current. Of course, there are several different effective constants from N1 to N9, which depends on the shapes which we analyze. Okay, and we calculate that shapes that constants to have right equation of motion for our analysis into numerical model. And we of course have to introduce some relation to the Young modulus and the this inertia of moment, because we've got here different distances of sorry, I have to okay, there is neutral axis one can see, and we have to have the proper calculated the Young modulus, which is equivalent wedged area inertia moment of both magnetostrictive and substructure beams, and it depends of this distance HS and HM, which is shown here. HS is this distance between the neutral axis of fall beam and only the part of the magnetostrictive, but HS is the distance of the neutral axis and the central axis of the substrate beam. Okay, there we had the parameters as length, width, thickness, and several others, the density, Young modulus for both parts. We introduce such parameters as shown here. We have to find the optimal load resistance where the system generates the optimal, let's say, the highest value of the output power. And we made some analysis what kind of power is received while we change the load resistance of the pickup coils, the subsystem of electric. And here there are several cases of the results, because we can see different thickness of the magnetostrictive beam and substrate, and there are some relations where M4 and S2 means the thickness of the magnetostrictive equals 4 millimeter, but S equals 2 means that this TS equals 2 millimeters. So it's changed. We have 4 cases, and we can see different value of this root mean square of power while we change these layers. Okay, so here to simplify the calculation, we assume that in the resonance area the modes can respond individually. These modes create a subspace where the nonlinear system response can be captured. And let's look at the figure B. The power outputs of 3 consecutive beam models is determined here for these three modes of the system, and one can see what is the differences. And the first position in the next figure A on the left side of the slide, illustrate the energy harvesting response for the analyzed beam thickness for these 4 cases. The system produces a relatively high power output for the thickness only for the case where the magnetostrictive beam equals 4 millimeter, but substrate was only 2 millimeters. But comparing with the results to the second mode and the third mode, it is negligible, I would say. Values for the second and third modes was much higher. And now here in this next slide, we have the second and finally here the third mode of the system. And in the second mode, the system intermittent behavior is generated in both the sweep up and down of excitation frequency of the beam vibration. So we analyze the system while the excitation frequency was sweeping up and next sweeping down. It corresponds of 2 types of solutions with different levels of harvested power. For the analyzed intermittent behavior, one can observe the sensitivity of the system to different boundary conditions with respect to the root mean square power output. So we can see that there are some values output, let's say, in such level, but in different way, for different boundary conditions, that this is much lower value. And this is it was observed for the second and the third mode of this on this model. Okay, and when the system vibrates in the first resonance zone, then intermittent effects didn't occur. We didn't notice any jumps between the two solutions for any of the investigated initial conditions. The power output reached a fixed value, and for the frequency, let's say 100 Hertz, one can see approximately 0.2 microvolts only, and it was found for some range of the initial conditions, boundary conditions. There is no different values. So only one response for that numerical model results. Okay, and here in this slide we can see the results for the second modes, and this behavior strongly depends on the boundary conditions. When the system reaches the excitation frequency of the high resonance areas, that figure B reveals the double solutions of the vibrating system in the vicinity of the second mode. It was taken for the 400 of excitation frequency hertz. And we received two different results, which depends on the boundary condition. So by introducing a center range of the boundary condition, one can observe significant differences between output powers. It was changed from 0.2, which is invisible in this figure, to, let's say, 0. Probably no, this is 2 to 8 microvolts. Okay, there are two results. Which one? The first one is, let's say, approximate 8 microvolts, but the second result is close to the 0. Okay, and the third mode case yields the highest output signals of approximately even 20 microwatts. Nevertheless, such power output can hardly be produced because the system often enters into a lower energy harvesting solution. One can see this blue color is lower energy harvesting. As can see here, there is many points. Many points where the results are very low on the very low level. So one can say, comparing these three results, that the second mode shape of the beam system is characterized by relatively convenient boundary conditions compared to the first and third mode cases. And for the analyzes range of the up and down excitation frequency sweeps through three resonance area, the middle resonance range yields relatively high sufficiency due to the occurrence of an intermittent phenomenon, I would say, only in the second mode. Okay, and we try to repeat such results in the labs. Unfortunately, our equipment was able to measure only in the range of the first mode, up to, let's say, 120 hertz. But if we put the highest value of the hertz, let's say 1000 or even 500, it was impossible to measure. So we get only results for the first mode, and we compare this to the numerical analysis. The values are similar, and even the range of the frequency looks similar. Let's say approximately 19 hertz. It was also 90 hertz, but it's only done for the first resonance zone. The second and the third we didn't receive, and we tried to change the excitation force from the base of the shaker. We analyze it for the excitation at 1G and 3G, and we after the sampling points, we can see if the system, when the system overcomes by the resonance, we can see the some increasing of the voltage output, and we can see the results for this two level of excitation. Unfortunately, this is only done for the first mode shape, and the case we analyzed the case of the beam while the system was of the beam when the substructure thickness was 2 millimeters and magnetostrictive beam was 4 millimeters, according to these results from this comparison, where we can see the most convenient proportion was while we have the thickness of magnetostrictive beam 4 millimeters and substructure only 2. Okay, so there was some, I would say, the analytical numerical results, and the next model I have, I'd like to show you only the experimental, but let's conclude this short results. So there were found optimal load level of the resistance while the system reached the highest energy harvesting efficiency. The next, the coin numbers has influence on the generator G, which converts the energy, and the energy harvesting efficiency strongly depends on the beam natural axis position, and the beam vibration in the vicinity of the second and the third mode strongly amplifies the energy harvesting level relative to the output power signal at the first mode, and the system reaches us in intermittent behavior while vibrating within the second and third resonance zone. The phenomenon of different solutions appears in these cases, which clearly depends on the boundary conditions. Yeah, it is worth noting that because of the nonlinearities, the sub or superharmonic solutions can occur in a similar frequency region, exerting a significant effect on the mode shape. Okay, so this is such a case of that model numerical of magnetostrictive part. And now let me show you the next one. This is concerning the energy harvesting, but in case of composite structure with mechanical movement limitation. I have made that experiment with my colleague from my department, Marcin Bocheński, who helped me very much in this measurements. And we did an experimental sets of parametrically excited vertical beam, where we attach the piezoelectric element on the beam. And we made some measurements, and I would like to show these results. So here I would like to present the electromechanical properties of the flexible composite structure, which is that beam. The investigation is provided for the mechanical system consists of a composite cantilever beam equipped with a composite microfiber element, which is connected here. On this beam, it is hardly visible here. Yes, and the tip mass, we additionally put here a tip mass, which was mounted on the free end of the beam. The composite beam was made of a carbon epoxy prepreg with plies configuration 45 degrees 00 and 19 and minus 45. It was 1, 2, 3, 4, 5 layers of this composite, and the energy harvesting estimation was realized by recording voltage on the piezoelectric patch mounted on the composite surface for various load resistance values. Okay, there is the parameter of this second our model. The length of beam was 320 millimeters. These dimensions are given here. The density, the Young modulus, Kirchhoff's, the tip mass is given. This is even much more weight that beam mass. Okay, so here we maybe have to back here. The structure operated at the parametric resonance since the excitation of the support was in vertical direction. So as is given here, the excitation was in vertical direction, where the beam axes were situated in the parallel to this direction of excitation. For the parametric resonance conditions, the excitation frequency was fixed close to the twice of the beam natural frequency of this beam. The natural frequency of this beam was approximately 3.2 Hertz. So we excited this model twice of this value to reach the parametric excitation in the resonance. And the condition of the system vibration are varied due to the mechanical limitation of the beam response by attached an external frame. So there is a picture of this frame which really was installed in vertically, but for our analysis in the high-speed camera, we put here a picture on the horizontal position. Okay, and while the excitation amplitude was increasing, the additional impact effects appeared and the disturbances in behavior of the beam occurred because this 0.7 touched the limiters, and this beam behaves different in the impact occurred or disoccur. Okay, so for impacting effect evoking, the mechanical stoppers are attached to the frame, while the free end of the beam vibrating horizontally. The marked points were used for the measurements of the composite beam response by high-speed camera. There are several marked points that we recorded that by high-speed camera. Okay, and there is maybe I'll try to put there is a movie while the beam vibrate without impacts. We can see there is no touch to these limiters of movement. One can see again. It goes right and back. There is no touch. And the second case of our analysis was while impacts occur. So now we can see a slow touch of this beam, the end of the beam of the deep mass to these limiters. Probably the touch was only in the right stoppers. One can see, okay, there is now, and we analyze how the beam behaves during the impacts occur and didn't occur, and what is the output power of this piezoelectric attached here while the beam behavior was different. Okay, so there were two coordinate systems used in measurements. The global coordinate system, which based on 2 points, the points 8 and point 9. It is connected to the frame and support. And the next coordinate system, the second one, was local, and it was started from point 1, and the axis goes through point 7. So this point 1 and 7. There were point of the local coordinate system, and point 8 and 9 the global. And we analyzed the position of these other points, how to find the behavior of this beam while the impacts occur and no. Okay, and here we've got the results of the displacements, these points from point 3, 4, 5, 6, 3, 4, 5, 6, and even 7. How the system behave, and here we've got the beam points of displacement in global coordinates shown, and there is excitation given here Q equals 0.62 G. That level gives there is no impacts here, and we can see some disturbances in this case when the beam vibrates, even if there is no impact. Now the next level of the excitation force it was 1.29 G, and at this level we received the touch. There was impacting on the beam, and we can see the differences between previous one when no impact and now when impact occurs. We can see that points from 4 to, let's say, 6 have we can say that here there are some high harmonics of these points. So we can see there are high harmonics of these points of this beam, but if the impacts occur, it looks more smooth, and the high harmonics is disappearing, I would say. So now in this slide, there is reported to response of the middle beam point, only 0.4. This 0.4 is given here in the middle of the beam, according to the global coordinate system, and the disturbances, the higher harmonics of the beam response are clearly visible. This is the red line of plot. Nevertheless, the fluctuation of the system response decreases significantly while impacting occurred. This is the black point. You can see what the differences by excitation Q equals 0.65 and 1.29. There is a black point is impacting, but red line is no impacting. You can see the fluctuation disappearing if the system touch this point. It's the same we've got for the 0.6 on this beam. Displacement of the another measurement point in this also in global coordinate system is demonstrated in this slide. This point is located close to the free end of the beam, and influenced on the higher harmonics of the displacement are hidden here, especially when observation is conducted in global coordinate system. But in the next slide, I will try to show you how it was measured by local coordinate system. We can then notice that there is visible differences if the system goes into impacting. This point is more smoother. This black points of this beam. Okay, now the same results, but we see this in the local coordinate system. So we analyze this position of this point according to the point 1 and point 7, and now we can see how it behaves. We can see more visible the beam points of displacement from 3 to 6. This is in local. You can see there is no impacting how the beam behaves, and now there is impacting. You can see this fluctuation is disappearing. It is more smoother here in this second case. So it's strange from my point of view, because I expect such results. I expect when system if system would not touch by impact, but here I expect the system in touch. It will be in touch, but the results was different. Okay, and now we can see the same of point 4 and point 6. If we've got the red line, we've got there is no impacting, but black line is with impacting. This is middle point of the beam, but the 6 point looks similar. If the impacting occurs, then there's no so much high harmonics visible on this vibration of this 0.6 or even 4. Okay, and next we try to measure the voltage output of the piezoelectric element for several levels of the excitations, and we gave here twice excitation frequency of the first mode. So this is 6.18 Hertz. It is twice value of the first natural frequency, and then we receive the parametric excitation in the first mode, and we can see how the system behave if we increase the force excitation. We receive a high value of the voltage received, and we can see in the next figure, the right figure, we can see several levels of excitation and the maximal voltage was received while the excitation was increasing. And finally, in this color green and red tells us that the impacting occurs, and we can see the resonance area is widened. There's more space where we can get the higher value of the voltage. It was done for the resistance 300 kilohertz. And here we've got the root mean square of power via excitation frequency for the same. We can see if there is no impacts, here is the resonance zone is very narrow, but if the impacts occurs, color green and red, we've got the widen area of zone of the first motor. We have from below 6 Hz to up to 7 Hz, the much higher value of the output power in comparing to the previous when the system no impacting. So we can say, let's say for a frequency, excitation frequency 6.5, we can expect two different solutions if the system are impacting or no impacting. The same root mean square of power is given how it behaves while the excitation amplitude is increasing. But from my point of view, the most interesting results is given in the left hand side of this plot. Okay, there is a given for different value of resistances, the voltage time series of root mean square and of power via excitation force. The energy harvesting was analyzed by different resistances from 50 to 900 kilohertz. There are some nonlinearities, but we use only this one green value, which responds to 300 kilo ohms for the previous results. I expect for different resistances we received similar effects of this receive the output power. Okay, so finally the conclusions: the range of structures operating is strongly dependent on the amplitudes of excitation. The limitation of boundary conditions allow to operating the system at parameters for much higher amplitudes of excitation compared to unlimited system. And while the vibration of the beam are smaller than boundary condition limitation, then the higher harmonic response are more visible, what was strange from my point of view. And higher harmonic components are reduced by impact of constraints. Okay, thank you for my short two presentations. And if you've got questions, so we can now, I give my